That's really yeah.
Oh, you have a lot of people online.
Oh, okay. Hello. My watch says it's 3:02, which I think means it's time to get started. I'm going to start calling people out, Eric. Okay. I am extremely excited to welcome our colloquium speaker for this week, which is Katherine Kleer. Katherine is an assistant professor of planetary science and astronomy at Caltech, where she has been since 2019. And prior to that, she was at MIT and then did her PhD at Berkeley. Katherine is a absolute expert in all things planetary processes, especially with JWST and ALMA. And she has done a lot of really impactful and awesome work, which she will tell us about today, and has been awarded with multiple prizes, which I will not list all of them, except to highlight that last year she won the DPS Harold C. Urey Prize for early career achievement. And with that, I will let Katherine talk.
All right. Well, thank you very much. And thanks for the kind introduction and for having me here. So my research is in solar system astronomy. So this talk will be kind of a blend of astronomical tools and kind of geological and geochemical techniques and fusing those together to understand solar system objects. Hopefully I will introduce all the jargon I use, but if I'm using a word that I haven't defined and that you don't know, please feel free to interrupt me so that I can clarify. And this image here is not directly related to the talk, but it's just to show, this is a recent image from the Large Binocular Telescope showing the kind of cutting edge of what we can get with ground-based observations on solar system objects. This is Jupiter's moon Io from the ground. And what I hope you take away from this and from the whole talk is just how much interesting geological and geochemical information we can now get using ground-based and space-based telescopes, and just the level of detail and the questions that we can ask about these objects. So the focus of my talk today is specifically on the thermal histories of the smaller solar system bodies, moons, and asteroids. So the heat flow of a planetary body is one of the real fundamental properties that drives how it evolves over its history, how it forms and evolves. It powers geological activity, it powers melting, even in some cases to the extent of differentiation, and is responsible for chemical changes. So broadly speaking, early in the solar system's history, the planetesimals, the kind of early pre-planets, were heated by residual heat of formation and also the decay of aluminum-26. Over time, we still have some of that remnant heat from that early period in the planets, but the smaller objects have been able to get rid of that heat very efficiently. They have too high of a surface to volume ratio. And so the smaller objects, a really significant heating term today and throughout the solar system's history, is heating by tides, for moons in particular. So this talk is going to focus on, or is going to kind of cover both of these time periods, the early solar system's history and then these processes of tidal heating, starting with these early planetesimals and then moving to understanding the history of tidal heating. So we'll talk about asteroids, the remnants of the planetesimals, and then go on to talk about moons and how we can study the long-term history of tidal heating. So the initial composition of solar system objects is first set by where they condensed in the protoplanetary disk. So I'll be talking about in the planetesimals, both their silicate content and their metal content. So the silicates that condensed out of the disk, starting from near the sun to far out, to 100 AU, let's say, this is the fraction of silicates in different mineral types. And so when you condense close to the sun, you're condensing crystal and olivines, and in particular, this mineral forsterite, which is the magnesium-rich end member of olivine. As you get a little farther away, you're condensing magnesium-rich pyroxenes, and then more iron-rich. And so basically, the two axes I'll be talking about are olivine and pyroxene, and then the magnesium to iron ratio. So you have higher magnesium close to the sun. And so this sets the initial composition of the planetesimals. So if they just stopped at that composition, you could look at the composition of the asteroids today and say how far from the sun they condensed. However, there are a lot of subsequent processes that occur that alter them. So they're heated by this decay of aluminum-26 primarily. This causes any water that they accumulate with, any water ice, to melt. So you can have cold water rock reactions, you can have hot water rock reactions. Those produce completely different types of minerals. And you can also have heating to the extent of full differentiation, even within these small planetesimals. So you have all of these subsequent processes that occur that are heating dependent. Then these objects that are potentially differentiated are catastrophically disrupted. You end up with all these little fragments. And that fragmentation is really useful to us because it actually means that we have all the pieces of the interiors of these objects, and we can back out these melting and differentiation processes that occurred. Okay, so this is like the broad context for the range of objects that we should have in the asteroid belt, which is the main repository now for this kind of silicate-rich material from the early solar system. And I'm going to be focusing for this talk specifically on this question of differentiation and how we can understand where it occurred and how extensive it was, how prevalent it was. And this question is of great interest to the planetary science community, enough that there's an entire mission that was kind of designed around answering this question, and this is the Psyche mission, and it is on its way to the asteroid Psyche, which was, so originally the asteroid Psyche and all of these M-type asteroids is what they're called, were thought to be the cores of these differentiated planetesimals. And I'll be kind of focusing the story here on how we're getting more information on these objects to broadly understand whether they really are these planetesimal cores, or if not, then what are they? And we'll, of course, get some detailed information on one of these objects from the Psyche mission. So broadly speaking, asteroids are studied primarily from their visible and near-infrared spectra. It's just a lot easier than any other wavelength range to get a ton of spectra in the vis and near IR. And these spectra, so these are like 0.5 to 2.5 microns for a range of different asteroid spectral classes. And we try to infer more compositional information from them basically by looking for meteorite analogies. So these are asteroid spectral classes, and these are different classes of meteorites. And so by looking at the comparison between the spectra, you try to kind of infer that an the other properties of an asteroid that are not visible in that spectrum through analogy to the meteorites. And this is fantastic, and we've been able to get a ton of information this way, but that information is also very limited. There are not many minerals that you can see strong signatures of in the near infrared. And in particular, when you look at the asteroids down here, all you really have is that their spectra are red. They're different degrees of red. They're different degrees of reflective, and sometimes there's a little bit of a spectral feature. But these M-types, these nominally metal-rich ones, you actually get no compositional information in the near infrared. Moreover, some of the exciting results in the past couple years in this field have shown that, in fact, the meteorite collection does not sample the asteroid belt very well, that most of the meteorites we have, which is how we think it's kind of our basis for interpreting the asteroids, is actually sampling the small number of asteroids that have undergone these major collisions in the past only tens of millions of years. Those are the objects that preferentially fall to Earth. So what the kind of exciting implications of that is that there are a lot of asteroids in the main belt that we don't have samples of on Earth of them or anything too compositionally similar to them. So that emphasizes the importance of getting more information. So you can get quite a bit more information than you have in the near infrared by extending to other wavelength ranges, and this is what I'll be talking about today. So this is in particular the mid-infrared, so mid-infrared spectroscopy with JWST, as you probably know from other areas of astrophysics, can give you great information on the mineral composition and in particular the silicate composition. And one key piece of information you get here is the minerals that are not iron bearing. So these features, these absorption features you see here are electronic transitions of the iron in the mineral. It's harder to see in the near infrared minerals that are not iron bearing, but you can in the mid-IR. And then you can get direct information on the metal content itself at radio wavelengths, both in kind of passive emission as well as in radar. So starting with the mid-infrared, we have been trying to build up a sample of asteroids, not just the M types, but I'll focus on that story today. With JWST, the actual JWST spectra from the MIRI instrument over the mid-IR, 5 to 25 microns are shown here. Most of what you see in this figure is just the thermal emission from the temperature distribution on the asteroid surface. So first you model that and then divide it out. And anything that deviates from flat tells you about the texture or the composition of the surface. So this is a collection of I think it's 14 asteroids now for which we have mid-infrared spectra. The bottom 8 or 9 of them are the M types. And to kind of broadly orient you towards these, if you've looked at like disk silicate spectra or comet silicate spectra, they actually all look quite similar, although the amplitudes of our features are a little smaller. So you see these dips here in the spectra. These are transparency features. These tell you that you have small grains or a highly porous regolith. So regolith is the term for the granular material sitting on top of a planetary surface. The maxima are specifically molecular vibrations in the silicates, and their exact positions tell you about whether the object is composed of olivine or pyroxene, and as well whether that olivine or pyroxene is magnesium or iron rich. And so you can see over the spectrum of these objects that they all look like silicates. I think that's the first takeaway. I'm not really going to talk about this one at the bottom. It actually is also silicates, and I have a comparison lab spectra in a few slides. It was much smaller, and it was in fact smaller than the diameter in the published literature, so it was smaller than we thought it was going to be. But it looks that way not because of composition, but because of surface texture, actually. Okay, so we can get the composition of the silicates from this the same way you would do for disks or comets. And we see quite a bit of variability. So I want to focus on the M types and what we learned about the M types. So if you recall, their near-infrared spectra were just red and featureless. When we look at them in the mid-infrared, we see these very clear silicate features. And so the kind of 0th order takeaway is that we're getting, that these things have a high composition of silicates. They're not just metal cores, right? They might have a high proportion of metal, but we're still seeing clear evidence of these, the minerals that they're made of. The mineral and, you'll notice also that these spectra are quite different from one another. I'll talk about enstatite and the few of them that make sense, which are probably these 1, 2, 3, look like this mineral enstatite. Among the other two, the other two sort of compositional types, these ones look more like the Trojans, which are these outer solar system small objects. These ones I don't even understand yet, but they seem to broadly group into these different compositional types, which is cool because it's telling us that these flat red spectra in the near infrared are actually hiding quite different compositional makeups. So this was kind of the purpose of extending to wavelengths that have more spectral features, is to kind of break this degeneracy when you have a featureless near IR spectrum. Okay, so we're seeing different compositional groups. All of them have silicates of some kind. The ones that we do understand look like this mineral enstatite. So that is this magnesium-rich, I thankfully added that plot back in. It's the magnesium-rich pyroxene end member that is supposed to dominate the silicate composition of these objects if they formed around 1 AU, so close to the sun, close to where Earth formed. But this is their kind of primitive composition, right? That these are not melted, altered objects. They are potentially just primitive objects that formed quite close to the sun. In order to match the spectra of these objects, we also need to use lab databases where the grains have been mixed with transparent material to simulate a very, very porous, fluffy surface. And in this case, so the asteroid spectra are in colors. The two black spectra are just lab spectra. They're not modeled. They're just straight lab spectra that provide good matches to many of the spectral features, and they are for this mineral enstatite. But you'll see that the spectral shape of the lab spectra is dramatically different dependent on surface texture. And I think this is important across silicate observations in all of astrophysics, that when you change the grain size distribution and you change the kind of fluffiness of the material, that it dramatically alters the spectrum. And so you need to take this into account because, yeah, these two lab spectra are the exactly same composition and just look different because of surface texture. So in addition to the presence of enstatite, we see that these are quite fluffy, porous surfaces. Okay, so at least the ones that the kind of 1/3 of these objects are consistent with this primitive composition that form very close to the sun. We can also get more information on them by going to radio wavelengths. So I now want to talk about that. So in the mid-infrared, we see the silicates. At radio wavelengths, you are uniquely sensitive to metal content. So metal content alters the spectral features at other wavelengths, but at radio wavelengths, including both active and passive, you can constrain the abundance of metal and even potentially what form it's in. So let me talk about that theory for a minute. The amount of emission that you get relative to a black body is strongly dependent on metal content. So this is the emissivity. As you increase metal content, you increase dielectric constant. And as you increase dielectric constant, you decrease emissivity. So a very metal-rich object might have an emissivity even below 0.5. In addition, we're looking at thermal emission at millimeter wavelengths from asteroids. The amount that emission is polarized should also increase with metal content. So with very metal-rich surfaces, you could have tens of % polarization to the thermal emission. What you actually get a constraint on is jointly porosity and metal content. So this is actually that 2D dependence. And what that dependence looks like depends on whether you have the metal in mineral form or in metallic inclusions. And I've given 2 pictures of meteorites in case that feels like a obscure distinguishing feature. So this is very iron-rich olivines, and you could have the same metal content, but you could, if you have a reduced composition, you could have all the metal in these little metallic inclusions, and then you need much less metal to depress the emissivity by the same amount. Okay, so we can measure the emissivity and the fractional polarization and say something about the metal content and potentially the form of the metal. The other thing that we'd like to do is actually look for heterogeneity in metals across the surface of these objects. So if you had a planetesimal that had differentiated, underwent some collision, it wasn't totally fragmented, you just kind of scooped off some part of it and exposed the metal-rich interior, you might expect to see some large-scale metal deposit on the surface. So with ALMA in particular, and the VLA at somewhat lower resolution, you can do all of these things. So you can measure the emissivity, the polarization, and you also spatially resolve the asteroids. It's actually really phenomenal spatial resolution. So these are animations, I don't know why they start in sequence, showing ALMA observations of thermal emission from 3 different asteroids. The asteroids are something like 200 kilometers in size, and the spatial resolution is about 30 kilometers. So it's pretty amazing to get this kind of resolution in thermal emission. And so we then want to interpret these observations to measure their emissivities. But because we're looking at thermal emission, and how much thermal emission there is also depends on how hot the surface is, you have to model and correct for that. So you may notice in the data, this is for Psyche, that this part of the asteroid is warmer. That's because that's the afternoon part. It's like rotating kind of like this. And so we model it with a thermophysical model, and this is the data minus model, and it actually does quite a good job. The residuals are not totally in the noise, which I'll come back to, but we can get a pretty good match. And then once we've kind of controlled for the actual temperature of the surface, you can measure the emissivity. So we've done this for 4 different asteroids now, the 3 that I showed you and 1 that I haven't made the movie for yet. And if you put the curves of the emissivities we measure on this porosity metal percent plot, you find that the 2 M-type objects, these supposedly metal-rich objects plot, as you might expect, they have emissivities of like 0.6, which is very low. Typically, we think of surfaces of having emissivities between 0.9 and 1, kind of at all wavelengths. But these are depressed to like 0.6. And then the S-type, which is supposedly metal poorer, as you might expect, kind of plots higher up here. But whether the form of the metal is in the minerals or metallic inclusions has dramatically different implications for how much metal you need in the surface. So I will argue that we can get some information on that based on the polarization. So for an emissivity of 0.6, like for the M types, okay, that's this colored curve, the fractional polarization should be something like tens of percent. However, when we actually look at these objects, we find that they have, in fact, almost no polarization, contrary to theory. So fractional polarization of at maximum 1%, and for one of these objects, there's no polarization at all detected. So my interpretation of this is that the thermal emission is polarized, but is becoming depolarized by scattering. And in order to do that, you need first of all, a low enough absorptivity material that you have a long enough like light path length in order to scatter multiple times. And second, you need highly efficient scatterers. So the way that you can do this is by having metallic particles in the regolith that are specifically of a size of like hundreds of microns to a couple millimeters that are very efficient at scattering millimeter radiation, and you embed them in an iron poor regolith. So this is actually quite consistent with the observations at other wavelengths. So that enstatite that I was showing you from the mid-IR data, that is an iron poor pyroxene, so you have a high path length. And then when you have that enstatite, it's in these reduced conditions where you put the iron in metal form instead of putting it in the silicate form. And so this actually fits very nicely with the picture we get from other wavelengths where you have this high metal content, but that metal is just in the form, is in these little conducting grains. So this is an image of an enstatite chondrite, one of these objects that has metallic grains in the mineral enstatite. And I think at least for a subset of these objects, we are really consistent with this picture of these objects that were one of the building blocks of the Earth. They condensed around 1 AU. But this isn't the entire story, right? Because I showed you that only 3 of the 9 M types look like enstatite. And I want to come back to what I said here, where, you know, I said the residuals are pretty good, but they're not exactly in the noise, right? And the fact that they're not in the noise, not exactly in the noise, is actually telling us about the heterogeneity across the surface. So because we have every point on the asteroid at most times of day, we can actually pull out the emissivity and the thermal inertia that controls the temperature versus time of day for each location and make a map of that. So we can look for these heterogeneities. And I think the results for Psyche are actually less interesting, and I'll focus on Calliope. What we find for Calliope, the second of the two M types that we observed, is that there's one region on the surface that has super low emissivity, which corresponds to very high metal content. Related to this, or at least I think related to this, is the composition of Calliope's moon. So when I was showing those three movies, you might have noticed that there's this little object, that there was this little object up here that is orbiting around Calliope. So that's Calliope's moon Linus. We did not discover it. It was discovered in the 90s by adaptive optics. But we resolve it in thermal emission. And that moon is substantially less metal rich than Calliope itself. And so, while we can't like confirm that this is the correct story, it fits with a nice story that has been proposed based on the dynamics, the orbit of Linus, that a giant impact, or like a small scale analogy to a giant impact, collided with Calliope. It liberated a bunch of material, and if Calliope was previously differentiated, that material would be coming preferentially from the outer layers of Calliope, basically analogous to the moon forming impact, right, but at a much smaller scale, and that the moon would have coalesced out of that upper material. And possibly we are seeing this excavation from that impact down to a layer that is more metal rich within Calliope itself. So it's a cool story. We can't totally confirm it, but it does fit together nicely with the dynamics. But the implication of this is, I just told you a bunch of these M types are like primitive enstatite chondrites, but this would be evidence that at least this M type is a differentiated object that has, a core and a mantle. And so I think, broadly speaking, let me kind of get to the takeaways. I think these M-type objects that had not been spectrally differentiable before, we're now getting the amount of detail to separate the stories, right? And say that some of them, but maybe fewer than we thought before, represent the interiors of differentiated objects. Some of them represent primitive objects that formed very close to the sun, and some of them may be something that we haven't yet figured out. And so by extending to these other wavelengths, we're getting this more complete picture, kind of unravel the stories of these objects. And I think, these techniques are applicable to all these other asteroid classes as well. And while the M types are uniquely interesting from this perspective because we had so little information before, adding the mid-infrared and radio to what we already had will give us allow us similarly to kind of unravel the story of all these additional spectral classes of asteroids. And broadly, I'm quite interested in just understanding the whole distribution of compositions that we have in the asteroid belt, hopefully connect these back to the observations James Webb is making of the same spectral features in protoplanetary disks even, and try to really unravel the history of the planetesimals in the early solar system. And then while the Psyche mission will give us fantastic information on one of these objects, given how much diversity there is within this spectral class, it's still important to make these ground-based observations and space-based observations to get the kind of broader context of these. Okay, so I want to switch gears a little bit here, although we will still be staying with the theme of using geochemical signatures to understand how something got heated and melted. But we're going to transition now from talking about asteroids to talking about moons, and from this kind of aluminum-26 decay heating to tidal heating. So this graphic is kind of an overview of the solar system's major moons. And as I mentioned at the beginning of the talk, these early heating processes are no longer very efficient at small objects like moons. And when you have a significant heat source in moons, that heat source is in most cases actually tidal heating. So This is not just a niche process. I have attempted to circle every object here that is tidally heated today and tidally heated in the past. Actually, a solar system scientist probably could debate with me some of these, so some of them I put in orange. But we think that this is a very prevalent process, both over the history of the solar system, like some of these past objects, as well as today, and even on exoplanets like the TRAPPIST-1 system that you've probably heard about, tidal heating and volcanism analogous to Io. So the place that this process can be studied the best is the Galilean moons, and this is partly because it's where this process is expressing itself most powerfully, but also simply because it is the closest moon system, and so it's the easiest to get detail on. So the Galilean moons of Jupiter, so Jupiter's over here, so moving outwards, Io, Europa, Ganymede, and Callisto. Io, because it's closest to Jupiter, is the most dramatically tidally heated, and those tides power volcanic activity. So what you're looking at here are volcanic plume deposits, sulfur deposits, silicate deposits, and even little lava flows all over its surface. So Io gives us kind of a unique place to study the process of tidal heating because the interior process is manifesting in such an observable way on its surface. We don't really get that with Europa. It's a little more subtle to tease out. So Io is kind of the laboratory that we use for studying this process of tidal heating that is so ubiquitous across satellites. And if you look at numerical models that people run for the formation of satellite systems, it's been seen in these simulations going back to Peel and Lee in 2002 that as you're forming the Galilean moons in the circumplanetary disk, you can capture them into the orbital resonance that is permitting the tidal heating to occur within tens of thousands of years. So just to get everybody on the same page, the tidal heating is occurring because of the orbital resonance between the three moons, Io, Europa, and Ganymede. So although the tides are ultimately coming from Jupiter's gravity, the thing that causes them is that the moons their orbits are not allowed to circularize because they're encountering one another at the same points every orbit. And so the gravitational perturbation of the moons on one another is adding up coherently and forcing them into elliptical orbits. So that means that they are experiencing a time-varying gravity field from Jupiter, and that's what's leading to the tidal heating. Basically, for the case of Io, it's distorting, kind of expanding and contracting every orbit. It orbits 1.77 days. That expansion and contraction is literally generating enough friction to melt the rock of its mantle, and melted rock is magma, and so that's what's powering the volcanoes. So you can capture these essentially immediately, right, into orbital resonance, tens of thousands of years after the beginning of the solar system. And this has some really interesting implications if true. So if you take Io's current volcanic resurfacing rate and you multiply that out over the entire history of the solar system, assuming that those models are correct, you find that the amount of material that has to have come out volcanically onto Io's surface over the history of the solar system must be tens to hundreds of times the entire volume of its mantle. And so in this case, Io is a very strangely evolved object. And we'd like to understand this history to see whether this is really true, to see how this has affected its chemical evolution. But Io's history is very hard to study because these same processes that are resurfacing its surface are erasing any record of its long-term history. So Io's surface is probably only recording the past million years. It used to be the case that there were no known impact craters on Io. At AGU a couple years ago, I saw a poster where one impact crater had been discovered on Io, and everyone at the poster was very excited. So now we have like a tiny bit of information. But what I will argue is that we can use the isotopes of sulfur to trace Io's longer term history. So sulfur has 4 stable isotopes. I'm only going to talk about the 2 most abundant ones, sulfur 32 and sulfur 34. So if I say heavy sulfur, I mean sulfur 34. And in particular, if you have a system that is recycling, if your sulfur is being recycled pretty efficiently, and you're preferentially losing one of those isotopes over time, then because this process has been occurring for so long, you can fractionate the whole reservoir can become slightly heavier or slightly lighter in terms of sulfur, the sulfur isotope ratio. Okay, so now I have to tell you a bit about what sulfur is doing on Io. And first I'll say Io does not have water or carbon dioxide. So sulfur is its primary volatile. So you can think of its sulfur cycle like Earth's water cycle or something. So broadly speaking, the sulfur is in these subsurface reservoirs. It gets incorporated into the magma. It gets outgassed from the volcanoes, so it goes on to enter the bulk atmosphere. From there, some of it gets lost from the upper atmosphere. And the material that gets lost from the upper atmosphere is preferentially, very, very slightly preferentially, the lighter isotope. What doesn't get lost ends up freezing back onto the surface. So during the day, Io's surface frost and atmosphere are in vapor pressure equilibrium, and then at night it freezes out. And so the material kind of ends up coating the surface, and then it eventually gets buried by lava flows or plume deposits, and it gets recycled. So you can just kind of push down the SO2 frost until it gets hot enough that it melts again. That's about 1 kilometer down. You can also react the SO2 with the silicates on the surface, produce sulfates, and you can recycle that much farther down into the interior. And so we think that the sulfur is undergoing this recycling both into the deep and shallow interior, and repeatedly passing through the surface reservoir where you are preferentially losing the lighter isotope of sulfur. So we have modeled this whole system. I will not go into any detail, but just to show you, this is what we think are all of the reservoirs of sulfur on Io. To the extent of the community's knowledge, we have quantified how big these reservoirs are. We've quantified, or at least put constraints on the exchange rates between these reservoirs, and this fractionation factor, which is the alpha on all of these, tells you how the isotopes are splitting between the 2 reservoirs as a result of this process. This is the easy version. So we take bulk Io, we differentiate it into the mantle and core, and actually almost all of Io's sulfur goes into the core. And in addition, the amount of sulfur in the core is probably the biggest uncertainty in this model. Okay, so it goes into the mantle, comes out volcanically, from there goes into the atmosphere, and it either escapes or it reaccumulates. So we can take this model, the one with all the terms in it, and evolve it over 4 billion years and see how the different reservoirs are changing. And basically, after running this whole model, you come to the conclusion that the primary term is what I just told you on the previous slide, that it's the fact that you're preferentially losing lighter material because you're losing from the very upper atmosphere, and you have a slightly higher ratio of light to heavy stuff in the atmosphere just by the different scale heights of the 2 different weights of molecules. That is the dominant term in how you're fractionating the isotopes. Okay, so we have this prediction, and as you would expect, you integrate this model over billions of years, and you find that Io's entire bulk reservoir of sulfur should be quite a bit heavier if this process has indeed been taking place for this amount of time. So now we want to actually go measure this, and we can do that with ALMA. And so since we're here at Space Telescope, I will also just show you, in theory, we can do this with JWST. This is a JWST spectrum of Io in blue here, and this is an SO2 band in the surface frost. This little guy here is the 34 SO2 band, and this little one here is the SO2 with 18 oxygen in it. which is cool. The reason that I'm not going to say anything more about this JWST spectrum is because this is the highest resolution lab spectrum that was available, and we are working on doing that at higher resolution, but with this type of lab spectrum, you can't actually interpret the line ratio in terms of an abundance ratio. So in theory, eventually we'll be able to do that, but we need better lab spectra because it turns out that James Webb is so much better than any previous instrument that the lab spectra were never needed at that resolution. So the data that I will be showing you are all from ALMA, where we are looking at the sulfur 34 not in the ice phase, but in the gas phase. So these are all observations of Io with ALMA, and I will orient you a little bit to what you're looking at here. These are two different nights of observation, and the little postage stamps are an image of Io's gas emission in specific molecules. So this circle is the size of Io. And you see, for example, especially down here, the primary SO2 isotopologue just traces the bulk atmosphere. So it is broadly uniformly distributed between upper mid-latitudes and lower mid-latitudes. The reason that it looks like there are these two spots on the edges is just a geometric effect because you're optically thin and there's a longer path length towards the edges of Io. Okay, so we looked at the sulfur 34 and 32 in the molecules of SO2 as well as SO. We also looked at NaCl and KCl gas. So these are salt gases that are exclusively present in Io's volcanic plumes. So you notice the distribution is super different, that these are just in these little spots that are probably, we think, individual volcanic plumes. So we looked at the chlorine isotopes in these two salt gases as well. And this is what the spectra look like. In order to interpret these, we need to use radiative transfer models because they have different excitation energies. We can't just take the ratios of lines. So we fit them with radiative transfer models. The free parameters are basically the gas temperature and the abundance. So we can measure the abundance or the column density of the 32 SO2 and the 34 SO2. We take the ratio of those, and those give us the sulfur isotope ratio that we present as our result. So what does that result look like? If you're a geochemist and this is meaningful to you, this is what the result is in the geochemist delta units. What this is telling you is that Io is 35 plus or minus 9% heavier or higher in sulfur 34 to 32 than solar system average as traced by sulfur in a specific meteorite. Okay, but to put that in context for people who don't think about sulfur isotopes every day, this is where Io plots relative to everything else in the solar system. So the sulfur is indeed extremely heavy. This is the 34 to 32 S ratio. It's heavier by far than everything in the inner solar system and is only matched by one molecule and one comet that has very high error bars. So this is consistent with this story where you've been distilling this collection of sulfur over Io's entire history. And I'll make a comment about chlorine. I'm not really going to talk about this chlorine result. Chlorine does participate in a similar process where it comes out in the volcanic plumes. It also gets lost. It's observed ionized orbiting Jupiter. And the plumes also resettle onto the surface. So there is a recycling process, but because there's so much stochasticity and because those fractionation factors are less well quantified, it's harder to turn this into a quantitative result the way that I'm going to try to do with sulfur right now. But broadly speaking, this kind of supports our interpretation of these heavy isotopic reservoirs telling us about a long-term history of loss. Okay, so aside from that qualitative conclusion that they're heavy and telling us about a long-term history of loss, can we do anything quantitative? So the situation that I've been describing, the scenario I've been describing where you have efficient recycling and incremental loss from a well-mixed reservoir, this is called Rayleigh distillation. And in such a scenario, you can use this equation to relate the isotope ratio measured today to the fraction of the initial sulfur inventory that still remains. And the key things you need to know are the starting isotope ratio, which we think we know from meteorites, to the precision, to well better than the precision that we need given the ALMA measurement. And then this fractionation factor, which is driven by the fact that you're losing material that's lighter by a specific amount. Okay, so by employing this equation, our sulfur isotope ratio measurement is telling us that Io has lost 94 to 99% of its available sulfur over its history. The word available is important here because we can only say something about the fraction of sulfur that's participating in the recycling and loss. We think that that's the mantle, crustal, and atmosphere reservoir. So we ignore everything that's locked away in the core. We think that's probably not relevant. But that Io has lost something like 95% of the sulfur that is not locked in the core that it started with, which obviously seems like a very high number and suspiciously close to 100%. So let's think about whether it makes sense. If you take Io's current mass loss rate, which is 1,000 to 3,000 kilograms per second, and you multiply that out over 4.5 billion years of the solar system's history, you actually basically get this number. So it corresponds really nicely, it kind of passes that sanity check at least. If you start with this number and calculating in the other direction, you find that Io has been losing mass at 0.5 to 5% its current rate over the history of the solar system. So we're quite consistent with this scenario where it's been roughly the same level of volcanic activity, outgassing, and mass loss as it is today. And we actually preference a scenario in which it was losing mass at a slightly higher rate over time. Our best fit value is more than 1 times its current rate. So our interpretation here is that Io has been volcanically active and therefore tidally heated for most or all of its history, potentially even more so at earlier times. And the implication of this has implications not just for Io's history, but also for the history of the other Galilean moons. For example, for Europa, if you want to think about the habitability of Europa and the relevance of tidal heating, that would be a heat input over its entire history, not just a current heat input. And is also really nicely consistent with these models that kind of show that you can do this dynamically from the beginning. So I think we'll wrap up on this note, this kind of the summary of the conclusions for the 2 different parts. Broadly speaking, we're trying to, extend the wavelength coverage on small solar system objects to get geochemical information that's telling us about the heating processes that have been going on in these objects today, as well as over the history of the solar system. I'm happy to take questions. Thank you.
Okay, questions. And for those online, I think if you type your question into the chat box, I should be able to see it and then read it out here. Yeah.
Very cool stuff. I was especially impressed by the 30-kilometer resolution on the asteroids. I was wondering, can JWST get physically resolved spectra of these asteroids? Can you put on the IFUs on these asteroids and get spatial information that way that helps answer the questions about the metallicity and porosity of the surface?
So should I repeat the question so they can actually hear it because it's...
Nope, they should be good because the ceiling mics are on.
Oh, good. Okay. Okay, so in thermal emission, so probably most of the time the answer is no, that it can't spatially resolve them. The problem is not exactly that it doesn't have the resolution, but that most modes at most wavelengths will saturate if you get the asteroid big enough that it could, in theory, be spatially resolved. There might be exceptions to that, like if you were looking somewhere that the reflectance is really low. If you were looking at like 4 microns or 3 microns or something, maybe if you looked at a big asteroid, you could spatially resolve it. But broadly, so I didn't really talk about this, but all the asteroids in my JWST sample are like 50 kilometers in size, because that's nearly as big as you can get without saturating MIRI at some wavelengths. And those are wavelengths that are important to me. So if you were just looking in certain wavelength ranges, you might be able to do it. But broadly speaking, sadly, it's saturation is a problem in the solar system.
Awesome stuff. Not my field at all, but I love the way you presented it. I'm curious about, though, the implication of this last scenario, that the very early start to tidal heating that's been pretty consistent after that. Does that also have something to do with the fact that it's primarily sulfur and not these other more volatile things, or is that an output of the planetesimal process way earlier?
Yeah, this is my current mission, is to answer that question. So the answer is we don't know. The people think that the Galilean moons formed out of a circumplanetary disk that can be thought of as analogous to the circumsolar disk, whatever. And so you could imagine that you were hotter closer to the forming Jupiter, and that there was an ice line somewhere, and that Io is inside of that ice line. So Io has no ice, Europa is like 10% ice, and Ganymede and Callisto are like 50% ice. And so there is a gradient, and that gradient could well have formed in the disk, but it also could have been the case that subsequent mass loss altered that ratio somewhat. And so the way that you would best answer this question at Io is by looking at the D to H ratio. The problem is that there is no hydrogen detected. So, but if you could fly a spacecraft through one of the plumes or something, you probably would see some hydrogen and measure that. I think you might be able to answer it from the oxygen 18 to 16 ratio, and that's what I'm trying to do. But I think it'll be a little more ambiguous because you're buffered by the oxygen and all the silicates. But yeah, it's not an answered question how much volatiles have been lost from Io and Europa.
We have an online question, so I'll read it from Katie Bennett, who asks, why is the sulfur reservoir so much heavier on Io than on, say, Earth, where there is also volcanism? Doesn't Earth also spew out sulfur via volcanoes, and presumably some preferentially lighter sulfur would be lost on Earth too?
Yeah, that's a great question. So having not actually run models for Earth myself, I'm a little bit hesitant to say what the most important term is. But there's a couple things. Earth's mass loss rate relative to the entire size of the reservoir should be smaller. And you potentially have less output of sulfur from the volcanoes. Sulfur is only the third most abundant, SO2 is only the third most abundant molecule that's outcast by Earth's volcanoes after H2O and CO2. So the chemistry is different when you remove those. But Earth is absolutely also recycling. It's recycling by a very different method, by plate tectonics, but you're certainly having that mixing and some amount of loss.
So can I ask two questions, one related to this and one to the first part of the talk? So here you say, so in your models of the sulfur cycle, you assume that all the heavy isotopologues go in and come out. So there's no assumption of a mechanism where some of the heavier isotopologues or isotopes can time, and then your isotope ratio will be even higher. That then changes our calculation.
I'm not sure I entirely understood.
I was thinking, like when you say, okay, so the S32 escapes, so you get enriched as 33, 34, whatever. All that material goes back in, but you're assuming that the same amount of isotopes are coming out, and there's no trap anywhere in the inside. Because that changes your F and your alpha.
Yes. So I guess a couple things. The loss, it's only slightly preferencing the sulfur 32. So you're still losing a bunch of 34. It's just that Yeah.
Yes.
But yes, we are assuming that we are in some kind of steady state, that you're not trapping the sulfur 34 preferentially somewhere else, but that you've achieved a steady state. And it's possible that there's some deviation from the steady state if you have sulfur that's leaching from the core into the mantle. But that would actually, if you kind of logic through it, mean that we would have to have lost even more sulfur to produce our result, because the stuff coming from the core would be lighter than the mantle, and so it's kind of pulling it the other direction.
And the second part is, when you go back to the first part of the presentation, when you selected your sample of M-type asteroids, were you expecting that diversity, or you were expecting that they were all similar, and all of a sudden they aren't similar?
The sample from James Webb?
Yeah, whatever sample you were using, James Webb, ALMA.
Yeah. Well, okay, so with ALMA, we're extremely limited because we have to use ALMA's most extended configuration, and it's only in that configuration for like 4 weeks every couple years, and you have to pick an asteroid that's at opposition at that time. And so that sets the ALMA sample. There's nothing more scientific than that. But for James Webb, so there are subtypes of the M class also in the newer taxonomies. It's called the X complex, and there's like the XEs and the XCs and the Xs. And so we tried to pick a range of those. But what's really interesting is that the diversity you see in the mid-infrared, it does not group into those spectral classes. So we weren't surprised to see the diversity. That was one of the reasons we observed so many, is because when they all just kind of look red and flat in the near infrared, there's a couple of different ways you can do that. I mean, you can do it with metal, you can also do it with carbon. And so they produce different albedos, but we suspected that those featureless spectra were hiding a lot of diversity, which is why we got so many targets. But we didn't know what we were going to get, right? Just that they were probably not all going to be the same.
I'll quick do an online question and then Steve. So Joel Green asks, is Io tidally locked to Jupiter? And yes. Does Io's surface have some extreme chemical mixing effects complicated by facing Jupiter so close?
Yes. Okay, so Io is tidally locked, and that all of that material that I've been talking about that gets stripped off of Io's upper atmosphere, most of it is becoming ionized, and it is, once it becomes ionized, now it's orbiting Jupiter at Jupiter's rotation rate. So Io's orbit is 1.8 days, Jupiter's rotation rate is like 10 hours, and so that material is all bombarding the trailing side of Io in its orbit. And so yes, this produces complicated chemistry. The reason I'm hesitating is because, in fact, Io has an ionosphere, and that ionosphere diverts the charged particles around so that for the most part, they are not actually bombarding the surface. You can have neutral particles, so there's recombination that occurs between the ionized material, and once it's neutral, it can get through the ionosphere and impact the surface. And so there are complicated things that can happen there. And so the two panels I showed you, there were two observations of Io. One of those was the leading hemisphere, and one of them was the trailing hemisphere. We did measure slightly different isotope ratios between the two, but they were the same within uncertainties. But this is something we're actually following up on, is we want to do now the sub-Jovian and anti-Jovian, the kind of other two sides, to see whether we see any differences there.
Okay, Steve.
That's a nice segue for my question, I think. So, you've been losing all this sulfur. There's the torus, the Io torus, the system. Is there any migration of all this sulfur to the other water-bearing bodies? And does that have any implication for life?
Oh, implications for life. I don't know if I can do that, if I can answer that last part. Okay, yes, there is absolutely migration of material from Io to the other satellites. As a maybe example, Europa's trailing hemisphere looks really red, and that red is probably coming from sulfur. And one of the theories for that sulfur is that it is being implanted from Io. That's actually only one of the theories. The other theory is that the sulfur was there already, but chemical reactions due to this plasma bombardment are the thing that's turning it to a form that is red in color. So I know that people talk a lot about these like oxides on Europa's surface, and if you can get them to migrate through the ice shell into the ocean, then that's something that life can exploit for chemical energy. And so I think the answer is yes, but I've never seen it very clearly demonstrated that you could in fact get those things to diffuse through the ice shell on any kind of useful timescale. Not my area of expertise.
A last question related to this. So you said that particles leave Io, right? They also reach Jupiter, and to my understanding, that's one of the sources of the aurora in Jupiter. I was wondering how these particles falling to Jupiter, producing aurora, are modifying the spectrum of Jupiter that we observe.
Yeah, that is a good question. So the primary place where you see those aurora are along the like flux tube, which is more or less the magnetic field line that passes through Io, and you see where that enters the Jupiter, and you'll see like a little footprint of Io. I'm not sure that they are altering the like total integrated spectrum of Jupiter. I know like when you have infall of comets into, this has been seen on Jupiter, and we're probably seeing it in Neptune as well, you can actually see that there's like the vertical profile of things like CO and HCN are very clearly linked to infall. I am not aware of that for the case of infall from Io, except for in the polar regions where the ionized material is moving in.
Any last burning questions?
I have a potentially very quick one. When you showed the different mechanisms for escape in Io, I saw them, if I'm not mistaken, all of them were non-thermal. Is thermal escape not important for Io?
It's not particularly important. I mean, I think, well, I don't need to go back to that slide. I believe that it is technically in our models, but it's such a small, it's like 3 orders of magnitude smaller than these plasma bombardment losses.
Okay, let's thank Katherine again for an awesome talk.